towards Casimir force measurements with optical tweezers?
First I would like to thank you all for coming here so early after dinner last night. And then I would like to thank Ogun and the organizing committee for inviting me. So I'm going to talk about this ongoing experiments at Rio, right? This is a picture of Rio. And since I am a theoretician, I think it's fair that I start by showing you the guys that are actually doing the experiment, right? So one of them is here, right? Is Ricardo, talking to you yesterday. And Luis is a graduate student. He's just beginning his doctoral research, and Vinay is a postdoc. So there are other people involved, but Yarini was a former student with us, with Nathan, which Nathan is a colleague of mine. He's an experimentalist. So Yarini was responsible for the early stages of this experiment, but she finished her thesis and went back to Mexico. Felipe is also here. He had a poster on screening, on Casimir screening, that is related to this project. We also have help from the Biophysics Institute in our university. Glauber is a student with Susanna. And we also have a lot of help from Gert Ingold. Some of you might know him. And his student, now former student, Stefan. So I will start with a brief introduction to optical tweezers and try to discuss the main features of optical tweezers so that we can understand what are the possibilities, what are the problems with using this kind of system for measuring Casimir forces. So this is an out-of-scale cartoon description of the tweezer. So we have this laser beam which is highly focused into this tight spot here. And then I have a microscopic particle which is trapped very close to the focus. And the objective, this is a microscope objective, should have a very high numerical aperture, and it also works not only to focus the laser beam, but also to produce the image of the particle we are trapping. Right? So it works both ways. So there is some light coming from the illumination of the microscope going from up and going through the objective downward. So why it works? I mean, it's important to understand that so that we can see what we can do and what we can't do. So usually the particles have sizes comparable to the wavelength, but I'm going to explain the physics of optical tweezers in this limit of ray optics when the particle is much larger than the wavelength. So in this case, we can use this picture of rays, right? So I have many rays crossing at the focus. These are the laser beam, the rays representing the laser beam. I'm just showing 2 rays here, but there are many others, right? So if I follow this photon coming here, if the bead has a refractive index larger than the medium, then I will refract that way that I'm showing here. So the z component of the photon momentum is going to increase. And then the sphere must recoil in the opposite sense. So because of refraction, there will be a force trying to bring the sphere center towards the focus. So this is a restoring force that is going to help us to trap the sphere close to the focus. But I'm not showing you here the reflected rays. So there is a probability that each photon is reflected, and if it is reflected, then it's going to push the sphere along the propagation direction. This is what we call radiation pressure. So you see that we need a few things, right? We need a relative refractive index larger than 1. I cannot trap bubbles in a liquid, right? I have to trap some object with a refractive index larger than the outside, the medium outside. But this difference cannot be very large, otherwise I would favor reflection instead of refraction. So if refraction helps, reflection is a problem. So you see that there is a fundamental issue if I want to use this to do Casimir force experiments, because to have a large Casimir signal, I want the opposite, right? I want a lot of reflection, right? So the Casimir signal increases with reflection. But fortunately, I can have small reflection at the laser wavelength and more reflection at the Matsubara frequencies I need to have the Casimir force. So it's not hopeless, right? But there is an issue here when using optical tweezers to measure Casimir forces. So another thing is that the particle must be transparent, right? If I absorb the photon, then I will favor radiation pressure again, right? Because I will transfer that linear momentum to the particle along the propagation direction. And I also need larger numerical aperture. All those effects are non-paraxial, so to have this restoring force in the dipole approximation, for instance, which is not valid here, it would be proportional to the gradient of E squared. So I need large gradients, so I need a large numerical aperture. So this is this parameter space here. I'm plotting the numerical aperture and the imaginary part of the refractive index of the sphere. And we compute here the region where I can trap using our theory based on me scattering in a very realistic model for the trapping laser beam. So we need a large numerical aperture, and the absorption coefficient must be small enough. So for instance, polystyrene, which is a very standard material for trapping, it's right here in this dashed line. And this was calculated for this size here. So polystyrene is really nice. I mean, it has a refractive index larger than 1, with respect to water. Trapping polystyrene in water works very fine. It's the standard trapping that people use. And we have this relative refractive index here. Another thing that works fine is silica beads in water too. It's also possible. This is the relative refractive index. And we can also drop biological cells. So a very nice feature of optical tweezers is that the stiffness, the trap stiffness is proportional to the laser beam power. So there is a knob, right? This is a very nice feature. I can tune the stiffness to the value I want in principle, okay? And so, this is very different from the AFM setup, right? That have a fixed stiffness. And I can have a very weak power and have a very small stiffness. For instance, the experiments I'm going to show you, the stiffness is of the order of a femtonewton per nanometer, which means that I can measure femtonewton forces if I'm going to measure nanometer displacements, right? So allows to measure femtonewton forces. This is the main advantage of optical tweezers. If I can measure very, very weak forces, I can, for instance, measure the Casimir force in principle for small spheres, or rather small spheres compared to other experiments, and rather large distances, and be well beyond the regime of validity of the proximity force approximation. So I would be probing this geometry of the sphere, right? Well, in this situation where the curvature plays a non-trivial role, right? So that would be interesting. Typically experiments that, well, we have been listening to them, right? Those last days, this ratio between radius and distance of the order of 1,000 or larger. And our goal is to have this parameter, this aspect ratio here, several orders of magnitude smaller, right? So we will be well beyond the validity of the proximity force approximation. So another interesting application is to investigate the role of screening by ions in solution. Remember that, actually I forgot to tell you that in order to have this refractive index not too large, I cannot trap in air, right? So I have to trap in a liquid. In this liquid, there will be ions in solution, usually. So I think this kind of setup is also nice to investigate the effect of screening by these movable ions for distances rather large. So, so this is the idea of the experiment. I have my trapped sphere, my trapped microsphere here. This is the laser beam, so it's trapped closer to the focus. And then I have another sphere, a larger sphere, which just sits on top of the cover slip at the bottom of my sample, right? And then I can move my cover slip, and I move the stage of the microscope. And I can change the distance between these two spheres. And if there is an attractive force, for instance, then this trapped sphere is going to be displaced laterally, right? So there will be, so my interaction force is going to be equal to the optical force. And the optical force is K, the optical stiffness, times this displacement that I'm not showing here. So if I know K, I can know the force, provided that I measure this displacement. Okay, so this is the setup. So I have my microscope here. So I have my laser beam coming here. I can control the laser beam power, I mean, by changing, by playing with the polarization and this polarizing beam splitter, and I measure the power I have. My laser beam goes upward from the objective. It's focused here. This is the view of my sample. And then I have the illumination from the microscope going down and making giving rise to an image here that I record in this camera. So this is a picture. So this red ray here, actually the laser ray is infrared, goes into the microscope, and that goes the objective somewhere here. We cannot see it, sorry, and goes up, and this is my sample, and this is the camera. So this is an image of an electron microscopy image of my spheres. So this is the big sphere that is going to sit on top of the cover slip, and these are the small sphere that is going to be trapped. I will have only one sphere in the experiment. Here in this image I have many small spheres, but I'm going to have just one. And we can measure these diameters, and we can see that they are very spherical. And this is a cartoon with the measured values for the trapped sphere and the big sphere sitting on top of the cover slip. So this is in scale now. We know to measure anything, you have to calibrate the stiffness, right? So the standard way of doing this is using the Stokes drag force when I have a relative motion between the sphere and the fluid and the liquid, right, and the water in our case. So I can do this in the following way. I have my microscope stage. I put it into motion at a velocity of microns, tens of microns per second, and then there is this drag force, which is proportional to the velocity of my stage. And this drag coefficient here is given by Stokes' law. Eta is the viscosity of water, of the liquid I'm using. A is the radius. And there is this correction due to the presence of the cover slip here at the bottom. So this is an exact result because we are in this regime of laminar flowing of the fluid. So it's a simple regime from the theoretical point of view. And then we can calibrate the stiffness by just measuring the displacement x. This we do with a single sphere. So this calibration we do before doing the experiment, right? So here there is a single sphere. And then we have this kind of measurement. Here we measure the displacement for different velocities, and from there we can, since we know beta, because everything here is known, I can know the stiffness. There are other ways of calibrating this. We can also measure the position fluctuations and measure the spectrum of fluctuations of position. And also we can compare with theory. We have a very realistic theory for this optical force. So this red line here actually is a kind of a band, right? It's the theory that we have developed, and this data here are obtained by Stokes calibration. And you see that, and there is no fitting here, right? all the parameters we measure independently. So there is a very good agreement, and so this is a third check. So there are many cross checks that we can do to see if the calibration is okay, including comparing with theory. And this is the bead size we are going to use. So you see that I have a stiffness of the order of 1 femtonewton per nanometer if I have 1 milliwatt. This is the typical value of stiffness we are going to use. So it's this point here. So what kind of interactions we are going to see in our setup, right? We cannot trap metallic particles, so this is a drawback in our setup. So we have to trap dielectric particles, dielectric spheres, and they are going to be charged usually, right? And also in the liquid there are ions in solution, and these ions, they are free to move, and they are going to move close to the solid sphere because there is a charge here, and they are going to form a sort of a layer around the solid charged sphere, and this is what we call double layer. So we can model this by writing the Poisson equation and taking for the charge density this value here is written in terms of this Boltzmann factors, right? So these ions are going to be placed according to this Boltzmann factors, and if this electrostatic energy is much smaller than kBt, then I can linearize these Boltzmann factors, and I get what people call linear Poisson-Boltzmann equation, which is like Helmholtz equation with an imaginary frequency. So this is somehow close to what you guys work, right? Because this kind of equation here. But here there is this characteristic length scale, which is the device spinning length, depending on the concentration of ions. So I can tune this by changing the concentration of ions. And this lambda d is simply the thickness of this double layer. Okay? And if I have two charged surfaces which are separated by a distance much larger than this device spinning length, which is this thickness here, then the interaction is going to be completely screened, because I'm going to see just the total charge, which is the charge of the surface plus the charge of the double layer, which neutralizes the charge of the surface. So the interaction is going to vanish, right? So it's screened away for distances larger than this typical, than this lambda d, which is the typical length scale important here. So this is the solution for a plane, right? But we can also write a solution for a sphere, for a single sphere. But in our case, we have two spheres, right? And then these double layers start to overlap if the distance between them is of the order of this thickness of the double layer, this is the device spinning length. So the charge density here, the distribution here at that point is going to depend not only on the presence of this sphere, but also on the presence of the other sphere, which means that I have to solve this linear Poisson-Boltzmann equation for two spheres, for the boundary condition of two spheres. But this is, for you guys, it's the kind of thing that you know how to do, right? I mean, we can write this potential in terms of these two separate centers, and in terms of these modified Bessel functions. This is very similar to what we do for Casimir, right? And here are the Legendre polynomials, and what we do is just to displace the origin, right? As we do in the scattering approach. So we have complicated expressions like this that then we can apply the boundary conditions and then calculate the force. So we have a model for this force, which is based on an exact solution of this linear Poisson-Boltzmann equation. And we can use different boundary conditions for this here. There is this constant charge model, which is the simplest one, but not very realistic. There is a regulation model, which takes into account the fact that the surface can exchange charges with the liquids. We can do different kinds of boundary conditions. So what about the Casimir force? So for the Casimir force, in this same setup here with our two spheres with these sizes that we are using, we can compute using the scattering approach, right? And this is the exact result take into account all Matsubara frequencies, and I'm here neglecting the screening of the Casimir interaction. The problem is that this is not a good assumption, right? Because these ions, they are going to screen not only the constant charge, the prescribed charge, but also charge fluctuations. The ions are also going to screen dipole or multiple fluctuations on each surface. So the Casimir interaction itself is going to be screened by the presence of movable ions. The problem is that nobody knows how to take that into account with some arbitrary geometries. I mean, there are results for parallel planes, but so we can compute here if I'm going to use PFA, but PFA here is a very bad approximation. So this is something open to, so you guys, if you want to open on that, this is an interesting thing to work on. Nobody knows how to calculate the screening of Casimir interaction for arbitrary geometries. But what we have done here is just assume that if I have no screening, distance is much smaller than the device screening length, I have the black line. And if I have strong screening, which is the opposite limit, I just remove the zero frequency contribution because these ions are not they are not going to be able to screen finite Matsubara frequencies, only the zero frequency. So I would have this blue line. You see that there is a huge, could have a huge. So the real case would be in between these two ones, these two curves. And the force, if actually now the results I'm going to show you are for distances larger than 400 nanometers, and you see that the Casimir force is very small, a few femtonewtons only. So our signal are going to be dominated by the electrostatic double layer force. So I'm not going to show you results for the Casimir force just for this double layer. And there is a small contribution from the Casimir, but this is just a few femtonewtons, as we can see from this plot, right? Because I'm going to consider distances larger than 400 nanometers. So this is the experiment set up again, and I have to run a bit. This is just to give you a flavor of how the experiment is. So this is the basic signal we have from the experiment, right? We have these films that from there we get all the information the information about the position here. So it's this Brownian fluctuation. From this Brownian fluctuation of this trapped bead, we can we infer the position and then the force. And this is the kind of result we get. These are results from last year. Now, this year we have better results, but we are still working on the interpretation. And so I decided to show the results from last year. So there is this Brownian fluctuations here. There is no apparent signal. And then there is this jump into contact in this region here. And then this part is trivial. It's just following this stage. I have to hurry. If I make 20 runs and average all of them, I have this kind of these green points here, and this yellow line is a smooth of this data. I'm doing some smoothing procedure here. So this is the total force, so the total interaction force. And here I'm going to focus on the double layer force because the Casimir is just a small contribution. It's just a few femtonewtons, 2 or 1 femtonewton. So I'm going to subtract from the experimental data the theoretical values for the Casimir force. And this is what I'm plotting here. So this would be now only the double layer force. So, and this double layer force is a function of distance, so I have this blue points. And this is the PFA for the double layer, very bad, right? Not PFA for Casimir, for the double layer interaction. And we fit our blue data with this linear superposition approximation, which is very simple. If these spheres are very far apart, then the double layers are independent of each other, okay? And then I just have this screened Coulomb interaction. Very simple formula I'm not showing. So I used this model to obtain these parameters, and then I compare with my exact calculation using the same parameters, and I see that actually, for shorter distances, the data start to deviate from the LSA. That's what I expect, right? When the double layers start to overlap, this linear superposition approximation is not good anymore because then the double layers are not independent of each other. There is this overlap. And then very nicely, my data try to follow the exact curve, right? So this exact curve, it's calculating using these parameters, and it shows that it's kind of working. So, but we would like to measure the Casimir force, so I don't have much time, but I will just mention a few things. So we need a strong Casimir signal, so I would like to discuss with you a few possibilities, but of course I'm very open to hear suggestions. So, there are a few drawbacks that we have to overcome. For instance, we have a difficulty in having reproducible experiments because these parameters that control the AA interaction, for instance, depend a lot on the sample preparation. This is something that we have learned over the years, over the 2 years we have been working on this. And also from the theoretical side, as I told you, we need the work. We have a lot of work to do because we need a theory that takes into account the screening of the Casimir interaction by the ions in solution. And another problem that I would like to mention is that since we have the Casimir force with a dielectric surface, we are very far from the saturation regime where the reflection coefficients are close to 100%, which is the case of metals, right? So the results are going to depend strongly on the dielectric properties of the material. So I need to know. So the material I have to choose, it's better to choose a material that I know very well, because if I change just a little bit the dielectric function, the force changes a lot because the reflection coefficients of the scattering matrix is going to change a lot. Another issue, we want to have a better Casimir signal. So one possibility is that the sphere sitting on top of the cover slip, well, it should not be necessarily dielectric, it could be metallic. So we can make a coating, right, a metallic coating. But you have to be careful that this coating must be very uniform. And this is related to the fact that I'm in a beyond PFA regime. If this coating is not uniform, as I am showing here, then I cannot just take this non-uniform nature and think of this as a roughness because of the size scale of the scales here. Because I'm beyond PFA, then this would be like having a local curvature radius, right, which is much more complicated and difficult to control. So if I do this coating, I have to be sure that this is very uniform. So it's a challenge to. Because on the other hand, if I were in the PFA, things would be much easier because I would average things out because of the length scales, right? So going beyond PFA, it's a challenge also in the sense that it's harder to control the experimental situation. So another possibility is to use a liquid metal, right? So we have been trying to use mercury for some time because we know how to prepare these mercury microdroplets. And these are some theoretical results that I'm not going to discuss now because I have very little time. But this is kind of difficult. I'm not going to discuss the problems that we have with this kind of setup. But maybe we could use another liquid method instead of mercury. And then I would like to discuss in the end this thing that perhaps we could do. Suppose we can finally measure the Casimir force. Then what kinds of applications besides going beyond PFA and discussing screening, we would like to do experiments showing the non-additivity of the force. And I think one of the most remarkable effects related to non-additivity is this geometric repulsion that this authors here. I think it's a very nice paper that perhaps the optical tweezer would be very convenient for doing this experiment for two reasons. First, because if I have a micro rod, it would naturally be aligned along the laser beam axis because the laser beam not only exerts a force but also an optical torque that aligns the rod along the laser beam. So I would align. So if I trap anything which is not isotropic, it's naturally aligned along the laser beam axis. So this is important in this proposal, right? And also in the optical tweezers, I'm able to measure very weak forces. The force here, this repulsive force, is very weak. So Unfortunately, it seems to be too weak for us at this moment. Okay, 2 or 3 orders of magnitude too weak. But maybe, I mean, I'm being perhaps too optimistic. Maybe in the future we could try to do this. So the idea is that I have this glass window here in the middle. Instead of a hole, I have a glass window, and if this glass matches the refractive index of the liquid, this would be more or less equivalent of having a hole. Okay? This is an educated guess, right? And we would need to compute and see if the force is really repulsive and how large it is in this kind of configuration, where instead of a hole, I have this glass window I have a metallized covers little with a window. So I will stop here because I want to have your feedback, and I'll just let this concluding sentence. Yeah, thanks.
Questions?
Hi, Paul. Thank you very much for the nice talk and very interesting results and experiment. I have 2 quick questions. One is more a remark concerning your last example with the hole. There is another result concerning this kind of geometry, which is probably more suitable for liquids. Instead of having a plane and measuring repulsion, by arranging the electric constants, you can have also attraction. And in the middle of the hole, you have that your object is actually trapped there. So you do not have instabilities. You actually have a passive trap that can be measured probably with an optical tweezer, or in similar ways. In reality, you also do not need the tweezer in order to trap your object, because the object is already trapped by itself. So the laser will be also a way of only a way of measuring the trapping or the position of this object. The second thing I was thinking, what about oxides like ITO for the little sphere? Because it will be transparent in the region of the laser, and it will be very reflective in the infrared.
Yeah, I think this would be a good idea. We are thinking about this.
And if I might say a last thing, when you use liquid metals, the fact that you have droplet liquid metals near a surface will not deform your bubble, your little sphere, so that it's no longer a sphere but more an ellipsoid. You see, because of the Casimir attraction.
Right. Yeah, that might be an issue, but we have to estimate that. We have done some experiments with mercury already. I'm not showing you here, but we don't see any deformation because we see the images, right? And, but maybe because this interaction is still too weak. If I had a stronger interaction, closer distances, then maybe there would be a deformation. But that might be interesting by itself too.
Mercury is repelled by the surface.
Sorry?
Mercury doesn't wet glass. It's repelled.
You mean the Casimir interaction?
No, mercury against the dielectric is repulsive. It doesn't wet. So it stays very nicely spherical. Anyway.
Some years ago, there was an elegant paper developed by Needham and collaborators on the interaction between 2 spheres of equal size. They were using an integral approach in the non-retarded approximation using bispherical coordinates, as far as I remember. Have you been looking at that? It should be very natural.
You're talking about the Casimir, the double layer, or
The Casimir form between 2 spheres.
There's a lot of work.
This we have done ourselves, but there are many papers on the Casimir interaction between 2 spheres. Yeah, I'm sorry I didn't mention all of them, but I guess you know, right? This has now with the scattering approach. I mean, this was one of the first examples of applications.
Even before, there's a long history of sphere-sphere.
You mean theory or
Theory, yeah, theory. We have all sorts of expressions valid. But what I wanted to comment specifically is the dissociable groups on the surface of polystyrene would lead to a very anomalous Casimir effect, which is due to monopolar fluctuation.
Right.
Which is usually not the case with dielectrics, where you start with the dipolar fluctuations. And that maybe would be more important contribution
Right.
to the experimentally detected force
Right.
than the other ones. So one should keep it in mind.
Yeah. We have to take a look at that, and maybe not use polystyrene if you don't want to focus on this monopolar fluctuation
Not need
induced
to focus,
interaction.
but if you measure
Yeah,
it, it's
yeah,
good.
we should take that into account at least. Yeah.
Galina?
Paula, when speaking about the dependence on the dielectric permittivity, the most important is not the dependence of the reaction coefficient, but the dependence on the dielectric permittivity of liquid
Right.
is exponential factor. And you have related ionic layers. So the dielectric permittivity of the liquid in this region will be quite different than the usually made.
Right, I see your point.
So, and the error in this value, uncertainty in this value, will give you the error much larger than your difference between the exit theory and PPA. And the theory of Casimir force here will be practically doubtful.
Yeah, you mean even if I use Lifshitz formula without the screening, there is this movable ions, and that would add something to
Sure,
the
the
dielectric
properties of the
function.
liquid will be quite different, and when you don't know the properties of the liquid, and these properties stay in the exponential factor, the small error in this value will give
Right.
very large.
Yeah.
But if you look at the first Matsubara frequency, at that frequency,
Yeah.
the liquid will not do anything.
Yeah, that's right.
This
This
is too
would be
fast.
what you were saying
For
is
liquid,
important
it's
for the zero frequency.
For ions.
Can we postpone this discussion for the coffee break?
Yes.
Thank you. Because we have a last question by Homer.
Just quickly, so I want to say thank you for your last slide. I think it would be totally awesome if we achieve our experimental proposal. So I'll report to my theoretical collaborators that we can expect results on that quickly. But just quickly, the version of the experiment in which the large sphere is coated with metal, would it be possible to also coat the slide with metal and then heat both the slide and the large sphere so you could observe out of thermal equilibrium Casimir forces between the warm large sphere and the small cool sphere?
Yeah, this is another thing that I think it would be important to yeah, this is another very interesting direction. If we, even with ITO that someone has proposed, there would be perhaps some heating, local heating, and then I would be in this sort of equilibrium situation. So that would be